When talking about electrophilic aromatic substitutions, the first thing that we need to understand is what kind of molecules are going to be involved in this mechanism. Starting off with electrophilic. So electrophilic, if we break down the word electro meaning electron and then philic meaning loving, we simply have something that is very electron loving. And then we have something that is aromatic. So remember that aromatic is simply something that exists in a ring structure and has those conjugated pi bonds. Now, here we have a benzene ring, which is the classic example of something that is aromatic, but we could have other aromatic molecules in this mechanism. And then lastly, this is a substitution reaction. This should not be mistaken with an addition reaction, because at first glance, when we look at this general equation of the reaction, it can look like an addition reaction because we have this benzene, we have something that is very electrophilic, and then our end product is just the benzene and that electrophilic molecule. So this can look like an addition because we just took this and we added it over here. But the answer to this is in the details. So if we take a look at the benzene, we have to remember that benzene consists of 6 carbons, and carbon likes to have 4 bonds. So if we take a look at this top carbon, it's going to have 1, 2, 3. Where's that 4th bond? That 4th bond is the hydrogen, because remember that in these line drawings, we don't include the hydrogen but we have to remember that they do exist. So each of the 6 carbons in a benzene has that hydrogen, and essentially what we're doing is that we're removing the hydrogen and we're adding in that electrophilic molecule. So we have the hydrogen, we remove the hydrogen, and we just added in that electrophilic molecule. If we did not remove the hydrogen, this carbon would have 5 bonds, and carbon does not want 5 bonds, it wants 4 bonds. Another thing that we have to make note of is that aromatic molecules, when they have these conjugated pi bonds that are delocalized, they are very stable. So it is not favorable to break these bonds down, break the aromaticity. So it's not favorable to break that aromaticity unless we have something that is very electron loving. That's where that electrophilic molecule comes from. We need something that is very, very electron loving, because if it really wants electrons, then it is more likely to disrupt this aromaticity, because this aromatic molecule is stable. So another thing that we have to make note of is that when we talk about these electrophilic molecules, they're going to have a positive charge. Why are they going to have that positive charge? We can actually think about that intuitively. So an electron is negatively charged. And if something is electron loving, it must have a positive charge, because once it gains that negative charge, it's going to move towards a net charge of 0. So that is why our electrophilic molecule is going to have a positive charge, and it's going to be very, very electron loving, so it can break that aromaticity. And then in the reaction mechanism, we'll see later on, is that after we disrupt the aromaticity and that hydrogen is abstracted, we will get that end product where we regenerate that aromaticity and we have that electrophilic molecule bound to our benzene ring. And that is essentially an intro into what electrophilic aromatic substitutions are. It involves something that is very electrophilic because we want to break that aromaticity. It's going to have an aromatic compound, and the key point is that this should not be mistaken for an addition reaction. We have to look at the details. We have to realize that there is a hydrogen here, and we're replacing that hydrogen for that electrophilic molecule.